Okay, so this is 30 seconds after I just stopped. So this is, I think I'm going to still say that this is 3a, because most of 3a is one example. So for scribing that, it's easy because you just have to typeset this. Okay, so how long does Karasuba's algorithm, I mean, if you use Karasuba's algorithm asymptotically, what time does it take? Well, let's say that t represents the time for Karasuba's algorithm. So I'm going to say Tn is the time to multiply two n-digit numbers using Karasuba's algorithm. Well, you actually, if you count, you have 5, well, you're adding numbers which are half n digits, so that takes half n time. So it works out that if you add everything up, you're going to do 3 multiplications of numbers which are n over 2 digits. Yeah, there's a ceiling and floor, so I don't care. Plus, and it works out if you add up all the additions and subtractions, it's going to take you about 5n time. Okay, so you have this relation that Tn is equal to 3Tn over 2 plus 5n. Okay, so let's solve that. So if we look at it, we say, okay, well, what is, we don't know what Tn over 2 is. Well, that's equal to 3 times Tn over 4. Right? So this is a recurrence relation. Plus 5n over 2 plus 5n. So this is equal to 9Tn over 4 plus 15n over 2 plus 5n. So now we can sort of keep expanding. So this is 9 times 3Tn over 8 plus 5n over 4 plus 15n over 2 plus 5n. So this is 27 Tn over 8 plus 45, just making sure I didn't make a mistake there, n over 4 plus 15n over 2 plus 5n. And so if we look at it, you say, okay, well, in general, what we're going to get is what we get when we keep doing this, we generally have 3 to the I t n over 2 to the I, and then plus some j is equal to 0, I minus 1 of 3 to the j times 5 times n over 2 to the j. So this is, I mean, how many times are we going to have, how many steps are we going to have until we get down to something we can evaluate easily? Because we say T1 is 1. Okay, so this is going to be about, how many steps do we do until this becomes 1? Well, about log n, log base 2 of n. So this is going to be something like 3 to the log base 2 of n, which we write lg. We write log base 2 of n lg. So this is going to be 3 to the lg n times 1. So this is 3 log n. And then this thing, this part, is equal to 5n minus 1 of 3 over 2 to the j. And then I'm not going to go through the whole solution of that, but this comes out to be 2 times 2 log 3. Well, okay. Actually, pause that. Put that on the side. So this is 3 log n. So this is 2 to the log 3 log n. And because these are multiplied by the rules of exponents, we can swap them, so we get 2 to the log n to the log 3, and so this is n to the log 3. So this, this, if you do all of this, then it comes out to 2 to the n log 3 minus 1 minus 2. Because this is just the sum of a finite geometric series, which you should know how to do from high school. Okay, so everything is order n to the log 3. Okay, so Karatsuba's algorithm, we say t. Now this is, I'm ignoring the ceilings and floors and stuff like that. But what you get is theta n to the log 3, which is, did I actually write down n to the log 3 somewhere? So n to the log 3 is slightly smaller than 2. I think it's 1.8 something, right? But it's smaller than 2. So it refutes, Karasuba refuted Kolomarov's conjecture. So now, in 1962, there was published, for the first time, an algorithm that did multiplication in subquadratic time. Which is a big deal, actually, when you think about it. Like, for thousands of years, we didn't really know how fast we could multiply. That's pretty basic. And now, so in, what you can do is say, okay, well, if you split it in 2, you get a speed up. What if you split it in 3? Well, it turns out that you can actually split it multiple ways, and then there are more complicated formulae. If you split it into 3, you get something called Toon-Cook 3, which Cook is Steve Cook, who is a professor at the University of Toronto, now emeritus, and he did this for his PhD thesis. He will come up again a lot in this course. So that's not, so you get a slightly better speed up. You get something a little bit less than 1.8 something. So in 1971, Schonage and Strassen got n log n, order n log n, log n. And then last year, in March 2019, Harvey and van der Hoeven got O and log n. And lots of people think that that's actually going to be the best bound possible for multiplying two n-digit numbers. So that was last year. It was kind of cool because maybe that was actually published then because I did it, I was teaching in the fall, so I sort of say, so when do you think we got the latest bound? Probably the ultimate bound, like 6 months ago. It was cool. So that is Karatsuba's algorithm. So now I'm going to tell you about Strassen's algorithm. Yeah, and this is going to be still 3a, I think. So, and then I have to record 3b. So Strassen's algorithm is similar, but for multiplying matrices. It's still divide and conquer, but now it's not. I mean, a number is a string, but a matrix is a two-dimensional thing. So you have to, how do you cut it? Well, what a mess. You see what I mean about it being similar. So this is Strassen's algorithm. So let's suppose you have two matrices, A and B, and you want to multiply them. So the idea is you can cut, let's suppose that they're n by n matrices, and n is a power of 2, so this recursion is nice. So you have A, which we're going to consider in 4 quarters. Which are A12, A11, A12, A21, and A22. B is B11, B12, B21, and B22. And then we want to get C, which is A times B, which is C11, C12, C21, C22. Okay, yeah, so C11, what is C11? Well, it's the first row of A times the first column of B, so it's equal to A11 times B11 plus A12 times B21. True? Yes. And then you go down until you get C22 is equal to A21 times B12 plus A22 times B22. Okay, so these, I'm sure you can multiply matrices. So these, you can work this out, so there's 4 of these. So if we do this, oh, right, I should say, start out by saying, what is the complexity? So you all know how to multiply matrices, right? To get entry ij, you take the ith row of the first one, the jth column of the second one, and you do a dot product of those two vectors. So that takes, these two vectors are of length n, assuming that you can do, assuming that the numbers are small enough that you can actually just do a multiplication, or you're working on a computer where the numbers fit in a machine word, so you can just do the multiplications in constant time. Multiplying these two vectors takes order n time. Okay? So an n by n matrix, multiplying two n by n matrices, so the resulting matrix has n squared entries, right? Because I goes from 1 to n, and j goes from 1 to n. So it's got n squared entries, and for each of those entries, you're multiplying two n component vectors. So it's going to take n cubed time. So normally, if you think about it, if you think about the normal algorithm you learned in high school, to multiply two matrices, it's cubic time in the dimension of the matrix. That's pretty slow, right? Because, so if you're multiplying two matrices of 1,000 by 1,000, this is going to take you time like 1 billion atomic operations, 1 billion little multiplications. So ultimately, yes, also Strassen's algorithm becomes practical when n is something like 1,000. Like, people argue about this because there have been changes in the architecture of computers. Some people say that the matrix has to be bigger than 1,000. Some people say no, it just has to be bigger than like 512 or something. But again, if you're working with really big matrices, you can do the first few steps with Strassen's, and then when the recursive steps get small enough, you just brute force it and use the algorithm you learned in high school. So how many? So here, to do A times B, normally we do one multiplication. So this is going to take, for each of these, there are 4 of these. We're going to do 2 multiplications and an addition. Notice that adding 2 n by n matrices still takes quadratic time, right? Because you're just, for ij, you're just looking at, for cij, you get by adding aij plus bij, which is like 1, assuming that the numbers are small enough. You can just add them in constant time. So you just have to do constant time work for every entry in C. So how bad is this going to be? Well, this is going to be n over 2 cubed, right? And you're doing 8 of these. So it's 8 times n over 2 cubed plus, and then these additions, this is going to be 4 times n over 2 squared. So this is just 8. So this is just n cubed plus n squared. So this is still n cubed. Okay, so again, like the first stuff this is like the first part of Karatsuba's, we haven't done anything yet. So what are we going to do? We're going to do like the same thing with Karatsuba's, where we find some sneaky way of rewriting things to reduce the number of multiplications. So now we can get rid of some of this. You can remember this, otherwise you can. So what Strassen said was, okay, let m, this is m is like z, m1 is a11 plus a22, you're going to understand why I took notes on this, times b11 plus b22, but they don't all have this nice, easy to remember form. That's why I've got the paper. m2 is a21 plus a22 times b11. I'm not going to, this M7. M7 is A12 minus A22. Straussen's algorithm, I think, is from 1969. So you can see he was inspired, I assume, by Karatsuba, times B21 plus B22. Okay, so these are taking place, and then, so you say, so this is a, okay, these are not taking place with the z's, these are, so you say C11 is equal to M1 plus M4 minus M5 plus M7. And then you go all the way down to C22 is M1 minus M2 plus M3 plus M6. So, these are 7 multiplications . Don't worry, all of the missing stuff is on Wikipedia and it will be in the scribe notes. 7 multiplications and 10 additions . Subtractions of n over 2 by n over 2 matrices. Okay? And then this is going to take, when you add them all up, it's 8 additions right. Okay, so it works out. It's because it's more than that. It's like 4 here. It's 1, 2, 3, 3 here, 3 here. But these are n over 2 by n over 2 matrices. So I think it's actually 16. Can't be 6. Anyway, it's a constant number. I should check this. It will be correct in the scribe notes. Additions, subtractions, 8. Actually, these are also, forget 8, this will be solid. N over 2 by n over 2 matrices. So, what you get that the recurrence turns into the time to multiply 2 n by n digit matrices is T n equals, notice, so there are only 7 multiplications. Before, if you do this naively, we're doing 8 multiplications, right? Because it was A11 times B11, A12 times B21. Okay, so for every row and every column, for every combination of row and column, we were doing 2 multiplications. But now, so that was 8. So now we're only doing 7. So at the cost of doing more additions and subtractions, we've reduced the number of multiplications. So we have 7 T n over 2. I'm ignoring ceilings. And then, so somehow, and then it's going to be some constant times n squared, where this constant depends on getting this number right. And if you do the same kind of expansion that we did for Karasubas, but just a little bit more carefully, you get that this is order n log 7, and then plus epsilon. Well, so it's little o of n to the log 7 plus epsilon for any positive constant epsilon. This is a little o of one thing. We'll talk about asymptotic notation next time. And this is O of n to the 2.8074. Okay, so, and it doesn't actually matter what, as long as this is a constant, you don't care, because asymptotically this is going to be bigger than n squared. Okay. So, again, as I said, it doesn't make sense to use this algorithm until n is pretty big. So n is not at least like a few hundred and probably 1,000 or something. So then there was also, so the current best, so that after Schoenage and Strassen, there were, did I say Schoenage? Right. I think before when I was talking about integer multiplications, I said Schoenage, but okay. So the current there were a bunch of algorithms got a little bit faster, a little bit faster, a little bit faster. Notice you can't go below n squared because that's the actual size of the input and the output. So the current best is order n to the 2.39 no, sorry, that's a 7 3 7 I think that's 28639 28639 and that's by Legal. That was from, I believe, 2014. So actually there was a big gap for about 25 years where I think it was Coppersmith and Weinberg. So they got down to some number. So for a while people thought it was 2.5, but then somebody got under 2.5, and then for a long time it was frozen at something, and then they managed to. So every time somebody shades like a tiny bit off this number, the theoretical computer science community goes nuts. But it is actually sort of an interesting question, because matrix multiplication is a basic operation. And it would be nice to know, sort of, this is called the matrix multiplication. This exponent is called the matrix multiplication exponent. It's like knowing sort of the gravitational constant. It's something that we think is fundamental. And also it turns out that multiplying matrices is used a lot, but also you can show that you can reduce problems to multiplying matrices. So any improvement in this implies an improvement in a lot of other algorithms, and you can also get reductions that go the other way, so that you can show that matrix multiplication, if you could lower bound this, then you could lower bound some other problems. Is that it? So that's 30 minutes. Okay. So that's kind of Super's algorithm and Strassen's algorithm. So next time we'll talk about the asymptotic notation, and we'll talk about the master theorem, which you need to which can solve things like this more easily than me expanding and trying to see the structure. Okay, cheers.